We've been talking about the slopes of these tangent lines. The limit as x goes to a of f of x minus f of a all over x minus a. Or my personal favorite, the limit as h goes to 0, f of a plus h minus f of a all over h. But it becomes cumbersome saying slope of tangent line, slope of tangent line. Well, there's a word for that, and that word is the derivative. We say that the derivative of f at a is the slope of the line tangent to the function at x equals a. Right? So essentially it's just the slope of the tangent line, but we don't want to say slope of the tangent line over and over, so we say derivative. And in Calc 1, we essentially study two things, the derivative and the integral, which is essentially a backwards derivative. So right here, just getting this definition, we'll spend a good portion of the rest of the course just understanding what this means, how it's used, various applications. So it's actually a very, very deep concept. Here's the notation for it. It's this f apostrophe a, right? We read that as f prime of a. Prime. That apostrophe is always read as prime. So we have two versions of the derivative here at a point a, and again we'll quickly get this to find a more general definition of this. So at point f, or at any point x. So don't completely become attached to this definition. We will very quickly generalize this in an upcoming section and use that definition from there on out. So this is only a stepping stone to get to the more general definition of the derivative, which replaces a with x, at least in the second version, which is the one that we'll be using to actually compute our derivatives. So let's focus on the h version, unless there's a very specific instance that comes up where we need it. So here we have it. We have f prime of a equals the limit as h goes to 0, f of a plus h minus f of a all over h. And very quickly we'll replace this a with x to get a more general definition. Let's do an example using the definition of a derivative, and we'll find that this works exactly the same as the examples we did using the slope of a tangent line. Well, of course they're the same because they're the same thing. So it'll work the same. It's just nice to have this new notation and word. Let's do an example. We have find f prime of negative 2 and the equation of the tangent line for f of x equals 4x squared plus 2x. Okay, well we know that when we find this derivative, that is the slope of the tangent line. Remember the equation for a line in point slope form is y minus y1 equals mx minus x1, so that m will be f prime at negative 2. And while this prime notation works great, we have another notation for the derivative. We could also write this as d by dx, or d dx, or the derivative with respect to x of 4x squared plus 2x. So we use this d dx notation often as an alternative to saying f prime of x. And we say this is the derivative with respect to x. And then we'd evaluate that derivative at negative 2. Okay, well let's get to it here. We need x1 and y1. We have x1, that's given because we're doing f prime of negative 2. So then y1 can be found by plugging this negative 2 into the original function to get our y value. So that tells us that y1 must be f of x1. Okay, so I'm plugging negative 2 in there. That gives us, what, 16 minus 4, so 12. There's our y1. Okay, so we have x1, we have y1. What do we need? Well, we need the derivative. We need the slope of the tangent line. So let's do that. So m tan we now know is the derivative, so we'll just write it as f prime of negative 2. All right, so limit as h goes to 0. Let's stick with the h version from now on for most applications. A is negative 2, so we have... Now, okay, so let me just note something real quick. Instead of writing negative 2 plus h and then squaring that out, I'm going to write that all these a plus h's as h minus 2. It's the same thing, I'm just changing it around. Okay, just a little side note there. All right, so we have, let's see, 4 times h minus 2 squared plus 2 times h minus 2 minus f of a. So that was f of a plus h. Now we'll do minus f of a. So that's going to be 4 times negative 2 squared. So that's times 4 minus 4 again. all over h. And then our goal is going to be to get this h down here in the denominator to cancel out. We want that gone. Why do we want it gone? Well, we're taking h to 0, so we don't want a 0 hanging out down in the denominator. Okay, well, it's just algebra from here. That's the good news, but the bad news is, unfortunately, algebra is the most challenging part of calculus. So let's do the algebra, right? No sure, they say calculus is where you go to master algebra, and then calc 2 is where you go to master calc 1, right? So let's see here. So 4 times, let's expand this out. We have h squared minus 4h plus 4. Let's see, plus we'll distribute this 2 now. 2h minus 4 minus 12. There, simplifying that inside those parentheses, all over h. Again, we're trying to get rid of this h in the denominator. So we want that gone because we can't divide by 0 when we take h to 0. Okay, let's distribute that 4 through to all the terms. So this is the limit as h goes to 0. 4h squared minus 16h plus 16 plus, let's see, 2h minus 16 there. 2h minus 16. And look at that, those 16s cancel all over h. And now we're getting somewhere because all our terms up top have h's in them, which means that our h in the denominator will cancel out. So let's see what we can do here. We have the limit as h goes to 0. Well, let's see. Well, there's 4h squared minus 14 all over h. Minus 14h. There we go. All over h. Okay, and then we can cancel this h, right? Make sure you cancel it. If you have it in the denominator, make sure you cancel it with each of the terms up in the numerator. So we get one of those squareds cancel, and the h cancels with that 14 there. So then we're finally ready to compute our limit. So we're still, let's write it one more time. Limit as h goes to 0 of, what do we have? 4h minus 14. And now we can compute the limit. I'm just going to plug in 0 for h. So I don't write the word limit anymore. That just leaves us with negative 14. Whew. So the slope of the line tangent to the curve f of x equals 4x squared at 2x at the point negative 2 is negative 14. That's what we've determined so far. Okay, back to our equation of the line. I scrolled it off the edge there, but it went something like this. Y minus y1 equals m tan x minus x1. And we decided x1 was negative 2 and y1 was 12. So plugging in then gives y minus y1. Well, we decided before that y1 was 12. So y minus 12 equals m, negative 14. X minus x1, we decided that was negative 2. So minus a minus negative 2. All right, then we just clean this up so we can write it in slope-intercept form. That's y equals mx plus b form. So y minus 12 equals negative 14x. Well, this would become positive 2 inside here. So positive 2 times negative 14 would be minus 28. And then adding 12 to both sides gives us y equals negative 14x minus 16. Final answer, there is the equation of our tangent line. The bad news is that some of these calculations can be very long and cumbersome as we do this limit definition of the derivative. But here's the good news. After we've convinced ourselves that we can do this process very well, we'll get some shortcut rules that will allow us to take this exact same derivative in about 2 seconds, literally. I'm not even exaggerating. So we're paying our dues now with this long method, and then once we get the power rule, for instance, we'll be able to do it in the blink of an eye. So just hang in there.